Right now, there's a whole wave of videos claiming scientists asked an artificial intelligence called Grok exactly how the ancient Egyptians moved massive blocks of granite, and that the answer it gave back left everyone terrified, or stunned, or speechless. Some versions claim the AI analyzed cutting marks at the Aswan quarry and arrived at a conclusion that shocked Egyptologists. One version even invents a specific research team, supposedly digital archaeologists from Heidelberg University, running an experiment in early 2025 that never actually happened. Other versions describe scientists feeding photographs of strange curved scoop marks found in the granite into the AI, only for it to conclude that no known ancient hand tool could have produced them, hinting at some technology history has completely forgotten. Every single one of these videos follows the exact same template, a dramatic claim, no named scientist you can actually verify, no real transcript, no institution that will confirm any of it ever took place, because none of it did. There's no verified session where any research team fed data into Grok and received back some world-altering revelation about granite. It's invented, recycled across dozens of channels, because a machine cracking an ancient mystery makes for a better thumbnail than the truth. And that's genuinely a shame, because the real answer to how Egyptians moved granite doesn't need a fake AI to make it compelling. It's already sitting in plain sight, carved directly into the stone itself, at a site any tourist can walk through today. And it was worked out by real archaeologists, real physicists, and real engineers, using nothing more exotic than close observation, careful measurement, and, in one particularly delightful case, a laboratory tray full of wet sand. Let's start with the material itself, because understanding why granite posed such an enormous problem for ancient builders is the key to understanding just how clever the solution actually was. Granite is an extremely hard igneous rock, and the ancient Egyptians, working during the Old and New Kingdoms, didn't yet have iron tools available to them. Their cutting implements were made of copper and bronze, metals soft enough that trying to chisel directly into granite with them would have done almost nothing beyond dulling the tool. Whatever method they used to extract, shape, and move blocks of granite weighing anywhere from several tons to, in the most extreme cases, over 1,000 tons, it couldn't have relied on simply cutting the stone the way you'd cut softer material like limestone or sandstone, which Egyptian workers did shape using copper chisels struck with wooden mallets. The answer to how they got around this problem is sitting, quite literally, exactly where they left it, at a site in southern Egypt called the Aswan Quarries, which supplied nearly all of the country's high-quality granite for well over 3,000 years, from the Old Kingdom all the way through the Roman period. And within those quarries lies one of the single most important accidental discoveries in the entire history of understanding ancient engineering. An enormous, still unfinished granite obelisk, abandoned exactly where ancient workers left it roughly 3,500 years ago, during the reign of Queen Hatshepsut, one of the relatively few women to rule Egypt as a full pharaoh in her own right. Had it been completed, this obelisk would have stood 137 feet tall and weighed somewhere around 1,200 tons, making it, by a significant margin, the largest single piece of stone ever attempted by ancient builders anywhere in the world, more than twice the weight of any obelisk that was ever actually successfully raised and erected in Egyptian history. It never got that far. At some point during the quarrying process, a massive crack tore horizontally through the center of the granite shaft, an unrecoverable structural flaw that forced the entire project to be abandoned on the spot. The workers put down their tools and walked away, and the obelisk has been lying there, frozen mid-construction ever since, its four sides still converging toward what would have been a distinctive pyramid-shaped tip at the top, exactly as originally designed. That accident of fate turned into an extraordinary gift for modern archaeology, because it means the unfinished obelisk preserves in complete and unaltered detail every single stage of the ancient quarrying process, exactly as it looked the moment work stopped. Archaeologists studying the site found that workers began by surveying and marking out the exact desired dimensions of the block directly onto the quarry floor, using string lines coated in red ochre pigment that were snapped against the stone surface to create precise, straight guiding marks, essentially an ancient version of a chalk line still used by builders today. From there, workers began excavating narrow trenches around and beneath the marked outline, isolating the block from the surrounding bedrock. At the unfinished obelisk specifically, those trenches measure approximately 75 centimeters wide, just enough room for a worker to physically stand inside the trench and swing a tool at the rock face. And here's where the actual technique becomes clear, because scattered directly around the site, exactly where ancient workers left them, archaeologists found hundreds of small, hand-sized rounded stones made of a different material called dolerite, a dark volcanic rock that happens to be even harder than granite itself. Rather than cutting the granite with a blade or chisel, teams of workers stood inside these narrow trenches and repeatedly slammed these dolerite balls directly into the rock face over and over, pounding the granite's crystalline structure into fine powder and dust, a few millimeters at a time. It wasn't cutting in any conventional sense. It was, essentially, controlled, methodical bashing, requiring teams of laborers working in continuous shifts for months on end to fully trench out a single large monument, producing what researchers have described as a deafening, continuous rhythm of pounding that would have echoed constantly through the quarry. Modern researchers have actually tested exactly how long this process would have taken using real experimental archaeology rather than speculation. Egyptologist Mark Lehner and several engineering colleagues conducted hands-on trials, physically pounding granite with dolerite balls to measure the realistic extraction rate, and their estimates suggested it would have taken roughly 8 months of continuous, dedicated labor just to fully free a monument the size of the unfinished obelisk from the surrounding bedrock. A separate, more recent photogrammetric study published in the peer-reviewed journal Advances in Archaeological Practice specifically measured the trench dimensions and pounding marks still visible today, confirming that dolerite hammering was indeed the primary excavation method used, though the same research also found physical evidence, ash and charcoal residue within the quarry, suggesting that fire may have been used alongside the pounding technique in certain situations. Heating the granite's surface and then rapidly cooling it with water can cause the stone to crack and fracture along predictable lines, since different minerals within the granite expand and contract at different rates when heated. And some researchers believe ancient quarrymen combined that thermal cracking technique with direct pounding to speed up the overall extraction process. Getting a granite block loose from the quarry and dragged a short distance on a sledge was only ever the first half of the journey. The real logistical challenge came next, moving that same multi-ton block, sometimes well over 100 miles, from the Aswan quarries in the south all the way down to construction sites like Giza, near modern Cairo. Egyptian engineers solved this using the single most efficient transportation resource available to them, the Nile River itself, flowing north through the entire length of the country and providing a natural highway that required no roads, no wheels, and considerably less friction than dragging stone across open desert. Blocks destined for river transport were loaded onto large wooden barges, specifically constructed and reinforced to handle enormous concentrated weight. Researchers studying ancient Egyptian shipbuilding techniques have found evidence that builders sometimes used a technique involving a thick rope truss running the length of the vessel, tightened to counteract the hull's tendency to sag or bend under an extremely heavy, concentrated load, a genuinely clever piece of naval engineering for a civilization working entirely without metal fasteners or the kind of rigid keel structures used in later shipbuilding traditions. Timing these river voyages also mattered enormously, and evidence suggests Egyptian builders took full advantage of the Nile's annual flood cycle, when rising floodwaters temporarily extended the river's reach much closer to construction sites that would otherwise sit a considerable distance from the main channel during drier parts of the year, shortening the difficult overland portion of the journey on both ends. Once a block had been fully separated from the surrounding bedrock, an entirely different challenge began, actually moving something weighing dozens, sometimes hundreds of tons across miles of open desert all the way to the Nile, where it could be loaded onto barges and floated downriver to wherever it was ultimately needed. This is the part of the puzzle that remained genuinely unresolved by modern science for the longest time, and its eventual solution came from an entirely unexpected place. A 4,000-year-old tomb painting, and a team of physicists working in a laboratory in the Netherlands nearly 2 centuries after Egyptology first became a serious academic field. Located at a site called Deir el-Bersha, roughly 320 kilometers south of Cairo, and dating to roughly 1880 BC, archaeologists had long known about a striking wall painting depicting 172 workers hauling an enormous stone statue using ropes attached to a large wooden sledge. For generations, one particular detail in that painting puzzled Egyptologists. Standing at the very front of the sledge, positioned just ahead of the massive stone load, is a single worker, shown pouring liquid directly onto the sand immediately in front of the sledge's path. For years, the dominant interpretation among Egyptologists was that this act was purely ceremonial or ritualistic, water poured as some kind of symbolic blessing, rather than serving any actual practical physical purpose, a reading reinforced by the fact that earlier experiments with wet sand, conducted without properly controlling for the specific moisture range involved, had actually suggested that adding water to sand should increase resistance rather than reduce it, seemingly contradicting the idea that the painting depicted any kind of genuine engineering technique. In 2014, a team of physicists, led by Professor Daniel Bohn at the University of Amsterdam, decided to actually test that assumption experimentally, rather than simply accepting the ceremonial explanation on faith. Publishing their findings in the peer-reviewed journal Physical Review Letters, under the straightforward title, Sliding Friction on Wet and Dry Sand, Bohn's team built a miniature laboratory version of the Egyptian sledge and systematically tested how much force was required to drag it across trays of sand under carefully controlled conditions, comparing completely dry sand, sand with varying amounts of added water, and sand that had been oversaturated. Bond later explained to reporters that the central question driving the research was simple. Egyptologists had assumed the water pouring was purely ceremonial, so his team wanted to actually find out why, if anything, the ancient Egyptians might have really been doing it. What they discovered directly validated exactly what that 4,000-year-old tomb painting seemed to be showing. When researchers dragged their test sledge across completely dry desert sand, loose clumps of sand would build up directly in front of the sledge as it moved, creating a small mound of resistance that actually increased the total force required to keep pulling it forward. But once the researchers added a specific moderate amount of water to the sand, something changed at the microscopic level. Tiny capillary bridges, essentially small droplets of water surface tension, formed between individual grains of sand, binding them together and making the overall surface noticeably stiffer and more rigid. In exactly the same way, slightly damp sand is what actually allows you to build a proper sandcastle, while completely dry sand simply crumbles apart. That added rigidity meant the sledge no longer sank into or displaced the sand beneath it nearly as much, dramatically reducing the friction the workers had to overcome with each pull. The actual numbers involved were substantial. According to Bond and his colleagues' published measurements, adding the correct amount of water to the sand reduced the necessary pulling force by roughly half compared to completely dry sand, meaning the ancient Egyptians could have hauled the exact same massive stone load using only half the number of workers, or alternatively, moved considerably heavier loads using the same workforce they already had. Bond was careful to note that this wasn't simply a matter of adding as much water as possible. Sand that becomes oversaturated actually behaves differently again, and the friction-reducing benefit only holds within a fairly specific, optimal range, estimated at somewhere between 2 and 5% moisture content depending on the particular composition of the sand itself, which is exactly why the tomb painting shows a dedicated worker whose entire job appears to have been carefully managing that water application, rather than simply dumping buckets indiscriminately in front of the moving sledge. Bond's research team was also direct about the significance of debunking the old ceremonial interpretation. Egyptologists, he noted, had generally assumed that pouring water in front of the sledge was purely symbolic, a ritual gesture with no functional purpose. His team's physical experiments, grounded in genuine, measurable, replicable physics, demonstrated instead that the Egyptians were almost certainly using a real, practical engineering technique, one sophisticated enough that it remains genuinely useful for understanding modern granular material behavior today, since sand, gravel, asphalt, and similar loose materials still account for a significant share of global industrial material handling, and the same friction principles Bond's team documented apply directly to modern engineering challenges involving exactly those kinds of materials. Getting a granite block loose from the quarry and dragged a short distance on a sledge was only ever the first half of the journey. The real logistical challenge came next. Moving that same multi-ton block, sometimes well over 100 miles, from the Aswan quarries in the south all the way down to construction sites like Giza near modern Cairo. Egyptian engineers solved this using the single most efficient transportation resource available to them, the Nile River itself, flowing north through the entire length of the country and providing a natural highway that required no roads, no wheels, and considerably less friction than dragging stone across open desert. Blocks destined for river transport were loaded onto large wooden barges, specifically constructed and reinforced to handle enormous concentrated weight. Researchers studying ancient Egyptian shipbuilding techniques have found evidence that builders sometimes used a technique involving a thick rope truss running the length of the vessel, tightened to counteract the hull's tendency to sag or bend under an extremely heavy, concentrated load. A genuinely clever piece of naval engineering for a civilization working entirely without metal fasteners, or the kind of rigid keel structures used in later shipbuilding traditions. Timing these river voyages also mattered enormously, and evidence suggests Egyptian builders took full advantage of the Nile's annual flood cycle, when rising floodwaters temporarily extended the river's reach much closer to construction sites that would otherwise sit a considerable distance from the main channel during drier parts of the year, shortening the difficult overland portion of the journey on both ends. Even the final stage, actually lifting and positioning these massive stones once they arrived at a construction site, has its own well-documented physical evidence. In 2018, a French-Egyptian archaeological mission led by Yanis Gordon and Roland Enmarch discovered a genuinely remarkable system of ramps and staircases at an ancient quarry called Hatnub, used specifically for extracting a different valuable stone called travertine, also known as Egyptian alabaster. Unlike the simple straight ramps long assumed to have been standard across ancient Egyptian construction, the Hatnub system used a central ramp flanked by two staircases fitted with regularly spaced post holes. Evidence that workers used wooden posts and ropes to create a kind of pulley or leverage system, allowing a sledge to be hauled up a steep incline at an angle previously thought impossible using purely manual labor. According to the research team, this discovery suggests the Egyptians had developed considerably more sophisticated ramp and pulley engineering, specifically adapted to steep terrain, than earlier generations of Egyptologists had assumed, further reinforcing the broader picture of ancient Egyptian construction as a continually evolving, genuinely inventive engineering tradition, rather than a single fixed technique applied unchanged across 3,000 years of monument building. So when you put the full picture together, the granite quarrying at Aswan, the dolerite pounding stones, the possible use of controlled fire cracking, combined with the water-lubricated sledge technique documented in Jehuti-Hotep's tomb, the river transport by reinforced barge, and the pulley-assisted ramp systems confirmed at Hatnub, all confirmed by real laboratory physics and real excavation nearly 4,000 years later, you get a complete, physically verified, thoroughly unmysterious explanation for exactly how the ancient Egyptians extracted and transported some of the largest stone monuments ever created by human hands. No lost technology, no unexplained anomalies requiring an artificial intelligence to interpret. Just patient, physically demanding, remarkably clever engineering worked out by real people using the materials and knowledge actually available to them at the time, and confirmed by modern researchers using exactly the same rigorous, evidence-based methods that separate genuine scientific understanding from an invented headline. It's also worth acknowledging, honestly, that not every detail at the Aswan Quarry site has been fully, unanimously agreed upon by every researcher who has studied it. Some observers have pointed to certain smooth, curved, scoop-shaped marks found scattered around portions of the quarry, arguing they look considerably more precise and consistent than you'd expect from simple hand-pounding with dolerite balls, and a small number of alternative researchers, including engineer Christopher Dunn, have proposed that some kind of more mechanically sophisticated cutting tool might have been involved in producing those specific marks. Mainstream Egyptologists remain skeptical of that particular interpretation, generally attributing those marks to a combination of pounding techniques, tool wear patterns, and natural weathering over thousands of years. But it's a genuine, ongoing point of technical discussion within the field, openly debated using physical evidence anyone can go examine in person, rather than something requiring speculation about lost civilizations or hidden AI-derived truths to explain. That distinction matters enormously. Real, unresolved questions in archaeology get discussed exactly the way this one is, openly by named researchers, using physical evidence and published papers anyone can go read, sometimes reaching different conclusions from each other and continuing to test those conclusions against new evidence as it emerges. What doesn't happen, in any legitimate version of that process, is a single artificial intelligence chatbot being fed some vague description of ancient tool marks and spitting back a definitive, world-shaking revelation that conveniently no named scientist, no university, and no published paper can actually confirm ever took place. So the next time you see a video promising that Grok or any AI system has finally revealed the shocking truth behind how the Egyptians moved granite, remember what the real answer actually looks like: a still unfinished 1,200-ton obelisk lying exactly where workers abandoned it 3,500 years ago. Hundreds of dolerite pounding stones scattered across the quarry floor exactly where they were dropped. And a 4,000-year-old tomb painting that a team of real physicists in the Netherlands took seriously enough to test in an actual laboratory, ultimately proving that a single worker carefully pouring water onto sand was quietly performing one of the more elegant pieces of applied physics in the ancient world. That's not a machine's conclusion. That's real archaeology, real physics, and real patient human ingenuity, all still sitting there in the sand, waiting for anyone willing to actually go look.